All right. We've been looking at guess and check algorithms. We just took a little bit of a detour to look at floating point. And the reason we did it is that we want to come back to this idea of suppose we'd like to use guess and check to find, as we said, square roots or cube roots. In the case where we're dealing with integers, we could get away with this because we could simply generate all the possible guesses, there's only a finite number of them, and check them to see which one was the right answer or whether there was no answer if we basically went through all of them. When we start talking about trying to find answers, though, that are floating points, where the number whose cube root we're trying to find is not a perfect cube, we can't do the same thing. There's an infinite number of possible things that we could guess for, so we need to be more clever about it. And that's where we're going to use this idea of approximation. We could certainly still generate exhaustively a number of different guesses, all differing by a small amount. So we could start at 0 and then say, for example, do 0.01, 0.02, etc., for whatever small amount we might want to use, and use the same idea. But if we do that, in fact, we can't guarantee that we're going to get the exact answer. We'll just have to make sure that we're close enough. We can use that idea. So we can still use exhaustive enumeration. The differences now are we're going to take small steps, where we define how small a step size we're going to take, to generate all the guesses in some order. And when we check, the check now has to take into account the fact that floating points are not exact, and we just have to see if we're close enough. Well, let's look at that. Here's a piece of code to do it. Looks a little daunting, but it's not too bad. I'm going to do this for a particular value, trying to find, in this case, the root of 25. And I'm going to set a little value up here called epsilon, which is going to be my way of saying how close do I want to get. I have to pick a step size, which is going to say I'm going to start at 0, and then I'm going to keep going by increments or jumps of some step size. I'm going to arbitrarily pick the step size to be epsilon squared. We'll come back to that in a second. I'm going to do one other thing here. I'm going to keep track of how many times do I actually make a guess. So I'm going to set up a global variable called number of guesses, which I'm going to increment as I go through there. And I'm going to start off with my answer equal to 0. And then here's the idea. I'm going to use another one of these iterative loops. It's going to walk through it, and here's what it's going to do. It's first going to check to see, have I gone too far? What does it do? It says if answer squared minus x, if the absolute value of that is bigger than epsilon, okay, it says I have gone further than I can. Because remember, answer is going to keep increasing. If it gets to the point where it's bigger than that, it's gone too far. I'm also going to check at the same time to say, or rather it's too far apart. I'm also going to check at the same time to say, am I done or not? So this one is basically telling me, am I done? So as long as the difference between answer squared and x is too big, and I'm not done yet, I'm going to take another step. So I'm going to increase answer by step, and I'm going to keep track of the number of guesses I had here. And I'm going to keep doing that. So here's my generate test. I'm going to keep doing that until, in fact, my check, which is right here, turns out not to be true. And when that's not true, I jump out of it. I'm going to print out how many times did I actually guess. And then I'm going to check to see, is the answer close enough or not? All right. It's got that same basic form. This is an exhaustive enumeration, moving by step sizes, generating different guesses, and then checking them to see whether I've got something that's the answer I want or not. Let's see what happens if we try it. So over here, I've got that code. I'm going to do it with x equal to 25. And if, in fact, I now evaluate that, it takes almost 50,000 guesses. But it basically says that I get an answer of 4.999. It's pretty close to the square root of 25. Now, you know the square root of 25 is fine. This is okay that it didn't get the exact answer because I just want it to be an approximation. Now, what are some things that we might think about with this? Well, one of them is, how big a step size should I pick? It can be any small number, but one of the problems is if I make it really small, it's going to take a long time to find the square root. On the other hand, if I make it too large, I might skip over the answer without actually getting close enough. Let's look at a couple of examples of that. So I'm going to go in here, and I'm arbitrarily going to change this from epsilon squared to I'm going to take it as a step of, I don't know, 0.5. And I evaluate that, and I run it. In this case, I get lucky, because I actually got to the right point, I only got it in 10. But if I go back over here, and I don't know, I make this a really big step size, and I run it, says I don't find it after 13 guesses. Okay, so if the step size is too big, I might skip right by it. So let's go back over here and we'll make this, go back to being epsilon squared, which will just make life a little easier as we look for it. Okay, let's try a different number here. So we saw I could find the solution for 25 pretty quickly. Let's try something different. Let's make x, oh, I don't know, something big. And let's try running that. Oh, took a little while. It took, what is that, about a little over 1 million guesses, but it found a pretty good solution to it. Okay, it found that that's close to the square root of 12345. So, what does this say? Well, it says if we go back over here, in general, it's going to take x over whatever the step size number of times through the code to find a solution. And you can see that trade-off. If I want it to be fast, I'd like to make the step size large because that'll make this smaller. But if I do that, I might miss the answer. So I'd like to find a more efficient way to actually solve this problem. And we're going to do that in the next sequence.